Let's see what is problem number 11. Yeah, problem number 11 is two identical circular rods of same diameter. There are two circular rods which are of same diameter and are subjected to same magnitude of axial tensile force. So we have been given that there are two circular rods of same diameter. So there is one rod and there is another rod. They are of same diameter D and they are of same length also. So they are of same length. Let's say this is L and this is also L. One of the rods is made of mild steel, so this has E of 206 GPa. This particular rod E has 206 GPa, and this rod, the other rod, is made of cast iron. It has the Young's modulus of 100 GPa. Assuming both materials to be homogeneous and isotropic, and the axial force causes the same amount of uniform stress in both the rods, the stresses are within proportional limit also. So we have the same amount of P acting here because the area is equal, so obviously the stress will also be equal. So sigma and sigma both are equal stresses here. Now because this E is more, so obviously the strain is equal to sigma upon 206 here, and the strain is, or let's say this is strain 1 and strain 2, so this strain is sigma upon 100. So this is lower than this. This is epsilon 1 is lower than epsilon 2 because the original lengths are equal. So epsilon 1 into L is less than epsilon 2 into L, obviously. So that this is the change in length of 1 is less than the change in length of 2. So now the options are both rods elongate by the same amount. A is delta 1 is equal to delta 2. Option B is mild steel, which is delta 1, or the first material is elongating more than the cast iron rod. The option C is cast iron elongates more than mild steel rod, so delta 2 is more than delta 1. That's the third option. And fourth option, as the stresses are equal, strains are equal, strains are also equal in both rods. So epsilon 1 is equal to epsilon 2. So this is obviously wrong, and this is also wrong because strains are not equal, because the Young's modulus are not equal, so the elongations will not be equal. And because the Young's modulus is lower for mild steel, for cast iron, which is second material, so the elongation will be higher in cast iron. So option C is right. This is right. This is C. This is A. This is B, and this is D. So that answer is C. Now the question number 12. What is question number 12? Question number 12 is the total area under the stress strain curve of a mild steel specimen tested up to failure under tension is a measure of. So the stress strain curve is like this, and it goes till the failure. This is a failure point. So the area under this curve, this is the area under the curve. What does this signify? What kind of information it provides to us? So the options are, the area is a measure of, or it is a reflection of the ductility. Second option is ultimate strength. Third option is, option C is stiffness, and option D is toughness. So let's see. First option is ductility. Second option is ultimate strength. Third option is stiffness, and fourth option is toughness. So option B and option C are outright wrong, because Option D, B, ultimate strength is this point. It has nothing to do with the area under the curve. It can be anywhere. Similarly, the stiffness is nothing but the tangent to the curve, and that also has nothing to do with the area under the curve. So that leaves us with two options: ductility and toughness. Now, ductility and toughness are both related terms, but the technical term for this area is toughness. Ductility is a measure of its toughness, or how much it can, how much let's say how much change of length it can take. So the area of it is not directly related to the area under the curve. It just is related to how much strain, plastic strain rather, it can take. But the area under the curve is directly proportional to the toughness, which means the energy it absorbs, and that energy is equal to this area itself. So the answer is D, toughness. So now let's see question number 13. The relationship between Young's modulus and bulk modulus and Poisson's ratio is given by. So E, K, and mu. Mu is called Poisson's ratio here. So what are the relationships, or what is the relationship? So option A is E equal to 3K 1 minus 2 mu. Option B is K equal to 3E 1 minus 2 mu. Option C is E equal to 3K 1 minus mu, and option D is K equal to 3E 1 minus mu. So here, even if you don't remember the exact relationship, you can deduce a few things. First thing is obviously the value of E. The value of E normally the value of E is normally higher, in the sense that it's like slightly higher than the value of the shear modulus, but that relationship cannot be used in case of bulk modulus. And the other thing is that, so that gives you a handle into that, you know, that we cannot directly deduce the value of K is lower than E. That gives you a handle that you know that you cannot use that relationship. But it also the other thing is that because E is like a linear thing and K is like a bulk thing, so obviously there has to be a relationship which has 3 in it. So right, but even that doesn't provide any handle here in solving this problem. So obviously whatever I'm saying doesn't make much sense. So obviously I will just tell the answer. The answer is the first one. Option A is the answer, and option A is E equal to 3 times K 1 minus 2 nu. That's the answer. So I mean, in such questions you have to obviously remember that the answer is that particular one. Let's see what is question number. Right. So the question number 14 is, a 1.5 millimeter thick sheet is subjected to unequal biaxial stretching, and the true strains in the direction of stretching are 0.05 and 0.09. Right. So that's a very, very good question now. So we have question number 14, which is like this. There's a sheet and it is subjected to unequal biaxial stretching. So there is some epsilon 1 here and some epsilon 2 here. We don't know what the values are right now. The true strains in the direction, the true strains means that the strains which are occurring because of the change of length, change of thickness considered during the equation. So the true strain, now that's a very good thing, is given by log natural of 1 plus engineering strain, which is nothing but log natural of 1 plus engineering strain is known as change of length over original length. Right, so this, please remember this equation. So when I'm given the true strain in one direction, that strain value is 0.05. So I know that this is first one. So the first true strain is 0.05. So that will be the change of, that will be log natural of 1 plus, let's say that change of length of first one is delta L1 upon L1, which is the original length of first side. So this is, let's say this is L1 and this is L2. Originally, these are the original lengths. So that gives me the value of the change of length along the direction 1. So how do I get the value of this delta 1 now, delta L1 now? So I invert this equation, so it becomes 1 plus delta L1 upon L1 is equal to e to power 0.05. Correct? So that becomes equal to, I just need to use calculator to figure out what is the value of e to power 0.05. So I just use the calculator here. So 0.05 inverse log natural is 1.051. So that becomes 1 plus 1 plus delta L1 upon L1 is 1.051. So I know that 1.051, this is 1.051, is the change of the length of first side. So 1 plus delta, or rather delta L1 plus L1, if I just do this, I just take this is equal to 1.051 into L1. So that becomes equal to, that is the first increased length. So this is the final length of the bar. I just corrected 1.051 into L1. So this is delta L1 dash, which means the increased length. Similarly, what will be the delta L2 dash? So we know that the strain in the true strain in the second direction is log natural of 1 plus delta L2 upon L2. So that is equal to that, or that implies 1 plus delta L2 upon L2 is e to power 0.09, which is nothing but, I need to use the calculator once more. So I use 0.09 invert log natural is 1.094. It's nothing but 1.094942. So let's see L2 plus delta L2, which is nothing but delta L or L2 dash final length in second direction is equal to 1.0942 L2. So now what is the, let's say that the volume initially was equal to its thickness. The original thickness is given as 1.5 multiplied by L1 multiplied by L2. That was the original volume. Volume final is some thickness T multiplied by L1 dash multiplied by L2 dash, and V0 is equal, or the V original is equal to V final. This relationship has to be used, and that gives us 1.5 into L1 into L2 is equal to T multiplied by L1 dash into L2 dash. That gives me 1.5 into L1 by L1 dash multiplied by L2 upon L2 dash is equal to T. This is nothing but 1.5. L1 upon L1 dash is, we can find out from this equation. So the L1 upon L1 dash is 1 upon 1.051. So this divided by 1.051 and similarly L2 dash upon L2 is 1.0942. So if I solve this equation, again I have to use calculator, so that becomes 1.5 divided by 1.051 divided by 1.0942 is nothing but 1.304. So that's the answer. .304. So the options are A 1.414, B 1.304, C 1.362, and D 289. So the option B is right. This is the answer. Option B. That's a very good question, and it requires a lot of fundamental understanding. So let's see what is question number 15. Question number 15 is question number 15. The stress strain behavior of a material is shown in figure which is now shown, which is like this. This is the strain and this is the stress. Now its resilience and toughness. So the strains are like this. So this is some 30, this is 70, this is 90, and this is 120, and this is 150. This is the way the stresses are there in the stress strain curve. And for the stress of 70, the strain is 0.004, and for the stress of 120 is, sorry, this is the 120 line, so the strain for that is 0.012. Okay, so we have this line. Now we have to find out what is the resilience and toughness. So we have to find out what is the value of resilience and what is the value of toughness for this material. So how do I find out resilience? Resilience is equal to this area, 1/2 sigma yield multiplied by epsilon yield. That is the resilience value. So that is nothing but 1/2 into 70 MPa, and the strain is 0.04. So it is 10 to the power 6 Newton per meter square multiplied by 0.0004. So if I just solve this problem, it's easy now. It is 70 into, this is 4 into 10 to the power minus 3 into 10 to the power 6, which is coming from 70 MPa by 2. So that is nothing but, this cancels out, becomes 2, and this becomes this becomes 70 into 2 is 140 into 10 to the power 3, or 14 into 10 to the power 4. That's the value of resilience. Now let's see the options provided. Now we'll first see the options. Option A is 28 into 10 to the power 4 and 76 into 10 to the power 4. Option B is 28 into 10 to the power 4 and 48 into 10 to the power 4. Option C is 14 into 10 to the power 4 and 90 into 10 to the power 4, and option D is 76 into 10 to the power 4 and 104 into 10 to the power 4. What is the answer? Obviously C is the answer. We know it without even solving further, because only that has 14 into 10 to the power 4 as the resilience value. Now let us see whether that is correct also by solving for the toughness. So toughness is the total area, like this. This is the toughness. So what is the toughness value? Toughness is equal to the total area. So that is nothing but the resilience, which is already calculated, 14 into 10 to the power of 4, plus the area under this trapezium here, this area, this area. How do I find out the trapezium area? It is half of the two heights, which is 70 plus 120, average of that, plus multiplied by the distance between the two lines, which is this line, this gap, which is nothing but 0.08. So that becomes this is 14 into 10 to the power 4 plus this is 70 plus 120 is 170. By 2 we can divide this by 0.04. So that becomes 170 into 10 to the power of 6, because it is megapascal, into 0.04. No, sorry, not 170, 190. So that becomes 114 into 10 to the power 4 plus this is nothing but 0.04 is 19 into 10 to the power, this 0 makes it 1 decimal less here, and 10 to the power 5 into 4. So that becomes 14 10 to the power 4 plus 19 4 is 76 into 10 to the power 4. So that makes it 90 into 10 to the power 4. So that's the answer, option C, because this is this and this is this. So option C, 14 and 90, they are the right answers. Question number 16. A concentrated force F is applied on the tip of the bent bar shown in the figure below. So how is the bent bar shown? So the bent bar is like this. There is a fixed end here. There is this bar arm, and there is another bar arm, and there's another bar arm, like that. This length is L, this length is L, and this length is also L. All the lengths are L, which means that these are perpendiculars here. They are perpendiculars. Now we have applied a force F here at this point, which is going inside the paper, plane of paper. So what is the load at a section close to fixed end? So we have to find out load here at this point, right? How do I find a load? So I transfer the force F here directly. So the F goes like this directly. So the reaction here will be F, and then there is a torque, because this F multiplied by this length will be acting as a torque there, FL. So those are the two things which are acting there, F force and torque of FL. Those are the two things. So what are the answers given? Answer A is force F, option B is F and bending moment of FL, answer C is F and twisting moment of FL, and answer D is F bending moment of FL and twisting moment of FL. So this is T equal to FL. So obviously answer C is the right answer, which is there is a force F and there is a torque or twisting moment of FL. And the last question, question number 17, is a thin walled cylindrical pressure vessel of wall thickness T and diameter D is filled with gas to a gauge pressure of P, maximum shear stress on the wall is then. So we know, and the options, first let's write the options. Option A is PD by T, option B is PD by 2T, option C is PD by 4T, and option D is PD by 8T. So now we know that the hoop stress is P into D by 2T and the axial stress is PD by 4T. And we know from the transformation of stresses that the shear stress is sigma H minus sigma A by 2, which is nothing but PD by 2T minus PD by 4T by 2. So that will be nothing but PD by 8T. So that is the answer. So answer is D, PD by 8T. So that is all about the problems which are there in chapter 1. And I request you to please solve many more problems, but these are the types of questions which will be appearing in GATE and the GATE questions are normally, rather I'll say, are not direct questions. They try to test your understanding of the subject very well, and if you have your fundamentals clear and you have solved a lot of problems involving good fundamental understanding, then you shouldn't have any difficulty in solving GATE problems. But I request you to solve as many problems as possible from many books, a lot of books you refer, and solve as many problems as possible, so that you have speed and understanding both come into picture at the same time, and those are both required in solving the GATE problems.